Welcome back to part 4 on this section where we are solving trigonometric equations. Here we have 2 cosine squared x minus cosine x minus 1 equals 0. And since it looks like it's quadratic in form, I'm going to go ahead and try and factor this thing. I'll go ahead and put a 2 cosine x and a cosine x respectively in each binomial. And then I know that if I multiply 1 times 1, I get 1. So now I just need to figure out how to get a negative cosine in the middle, which would be a minus on the second binomial and a plus on the first binomial's ones. That way I have 2 binomial factors. I'm now going to set those factors equal to 0. That will give me 2 cosine of x plus 1 equals 0 and cosine of x minus 1 equals 0. I'm going to solve for cosine x, and that will give me negative 1/2 on the right side. And then from there, I can solve for x by taking the inverse cosine of both sides, and then finding the value for which the angle is true. In the second binomial, again, I'll solve for the cosine of x function. I get cosine of x equals 1, and then I'll take the inverse cosine to get cosine inverse of 1, and that will give me the angle. From here, I just need to figure out where that is true. Remember, I'm looking at cosine for these, so negative 1/2 is to the left of 0 on the horizontal axes for my unit circle, and then I'm trying to figure out what this angle will be for which the x value is negative 1/2. And that angle is 2 pi over 3, but it could also be the angle down here in the third quadrant, which would be 2 pi minus 2 pi over 3. Now, keep track of this 2 pi. That would be meaning I would go all the way around. I'll do this in gray so you can see what I mean. I would go all the way around and then subtract 2 pi over 3, which would back me out to here, which is where the purple line is that I've identified as being in the third quadrant. So subtracting 2 pi over 3 from 2 pi will give me the other angle. And then remember that every time we go around the circle, we will bump into the 2 pi over 3 and also the 2 pi minus 2 pi over 3. So we need to think about these and reduce them, simplify them out. The first one will be 2 pi over 3 plus 2 pi k, or 2n pi. It just kind of depends on what textbook you're working with. And then the other one will be 2 pi, so I need a common denominator, which will give me 6 pi over 3, minus 2 pi over 3 will be 4 pi over 3, plus every additional rotation, or 2 pi k. So that takes care of the first set of solutions. Now let's look at when cosine of x equals 1. We know that cosine of x represents the horizontal direction. When it's positive 1, that means we're either at 0 or at 2 pi, which is the same location on a unit circle. That means that this solution for x equals cosine inverse of 1 is just going to be 2 pi k, where k is an element of the integers. And it's kind of assumed that that's what k stands for. A lot of times you won't see where k is an element of the integers, but it's not a bad idea to learn the notation and hear it all over and over and over again. So I'll go ahead and put that here as well. Looking at the next equation here, we have sine of 2x equals cosine x. The hint is to use trigonometric identities, and so I'm going to guess that the trigonometric identity we're supposed to use is something to replace this double angle, sine of 2x. Hopefully you recall that sine of 2x is equal to 2 sine of x times cosine of x, and that's still equal to cosine of x. Now remember, I'm trying to figure out where these two sides are equal to each other, and I'm solving an equation. This is not an identity where it says prove anything. So I'm going to take cosine of x and divide it by cosine of x on both sides. And notice that these equal 1 now. That gives me 2 sine of x times 1 is just 2 sine of x equals 1. And then I can solve for sine of x by dividing by 2 on both sides. That gives me sine of x equals 1/2. And if I look at my unit circle, I know that when the height in the y or vertical direction is 1/2, then I can find the angles for which this is true. The first one is in the first quadrant, and the other angle for which this is true is in the second quadrant. Now we just have to figure out how to represent that. If I want to solve for the angle x, I will have on the other side sine inverse of 1/2. And I happen to know that this angle where I get an output for sine is going to be pi over 6 plus, every time I go around the circle, I have to add 2 pi to that, which means I'll have 2 pi k as one of my solutions. So that is my angle that I put in kind of this magenta purple color. And then the other angle is pi minus pi over 6. That's going to equal 5 pi over 6 plus every additional rotation can be represented by 2 pi k. And that is my second angle on the sketch I drew. Again, we could also represent this with a sine function like this, where the sine function continues on to the left and to the right, and we're looking for where the corresponding height is 1/2. So you can see it's always in the positive region, and that relates to the solutions I found. In this last example, I have 4 sine of theta cosine of theta plus 2 sine of theta minus 2 cosine of theta minus 1 equals 0. Notice that there are 4 separate terms here, which means I'm probably going to have to factor by grouping. And so I'm going to look at the first 2 terms and say 2 sine theta is a common factor. And in the second grouping of 2 terms, I just see a -1 as my common factor. Now I need to figure out what's going to be left inside. And that gives me a 2 cosine theta plus 1 in the first groupings. And in the second grouping, I have 2 cosine theta plus 1. And I'm going to now factor those 2 common binomials out front. And leave the remaining stuff there. 2 sine theta minus 1. So my 2 binomials that I now have using factoring by grouping is 2 cosine theta plus 1 times 2 sine theta minus 1 equals 0. Now I'm going to set each factor equal to 0. And then I will solve each one respectively. The 2 cosine theta plus 1 equals 0, I just need to isolate the cosine or the trig portion of my equation, which will give me cosine of theta is equal to negative 1/2, which means theta is equal to cosine inverse of negative 1/2. On a unit circle, the location for which the angle would give an output in the negative x direction or horizontal direction would be at an angle of 2 pi over 3 plus 2 pi k, and also at an angle that is in the third quadrant, which is 2 pi minus 2 pi over 3. This will give me, as previously mentioned, a common denominator of 6 pi over 3 minus 2 pi over 3, which is 4 pi over 3. And then every additional rotation will be plus 2 pi k, where k is an element of the integers. And lastly, we have 2 sine theta minus 1 equals 0. I'll go ahead and solve this one for sine of theta. Sine of theta is equal to 1/2, and therefore we have a theta equal to sine inverse of 1/2. Now remember, that's looking at a vertical increase in the positive direction of 1/2. So I'm going to draw a horizontal line at approximately 1/2, and I'm looking for the location of those angles that will give an output of 1/2 for sine theta. And that will occur at pi over 6 and 5 pi over 6. So the answer to this is pi over 6 plus 2 pi k, and at 5 pi over 6 plus 2 pi k.